Hearty welcome to all knowledge seekers to my channel. This is Dr. Madhusudan Rao Kadapa. In some other videos, I have explained about the queuing parameters, their definitions, derivation of formulae, and so on, and some example problems. Now, in this video, let us have a look at a typical problem. Here, the problem is that there is a toll gate which is a single server one, which means like the toll gates in hill stations or pilgrimages where there will be only one toll gate will be there. So cars arrive at a toll gate according to Poisson distribution with mean 90 per hour, and average time for passing through the gate is 36 seconds. So here the mean arrival rate of cars or any vehicles is 90 per hour, and the service time is 36 seconds. Drivers complain of long waiting time. That is the problem. Authorities want to decrease the passing time through the gate to 30 seconds. So instead of 36 per each customer, if the authorities want to decrease 6 seconds of waiting time by introducing new automatic devices. But you know very well that implementing a automatic device will cost something, and this cost can be justified only if under the old system the number of waiting cars exceeds 5. In addition, the percentage of gates idle time under the new system should not exceed 10%. So can this new device, automatic device, be justified or not? This is the problem. So here we have the mean arrival rate of cars is 90 per hour, and mean service rate at the rate of service time of 36 seconds, it is 100 per hour. So using the relation for expected number of customers in the queue, LQ equal to lambda square by mu into mu minus lambda, on substitution we will get 8.1. So according to the given problem, the expected number of customers in the old system or present system is more than 5. So we can think of going for the automatic device, but the other condition is that the probability of idle server in the proposed system should not exceed 10%. Now let us check for the new service time of 30 seconds. What will be the probability of idle server? See, here we have for the mean service rate for service time of 30 seconds is 3600 by 30, which is 120 cars per hour. For this service rate, if you check the expected number of customers in queue, LQ equal to a lambda square by mu prime into mu prime minus lambda, on substitution we will get it is 2.25 for the existing rate of arrivals with a new service time, which is less than 5. Okay, anyhow the probability, we are interested in probability of the idle gate, which is equal to 1 minus lambda by mu prime, which is 0.25. That means 25% of the time the gate will be idle. So we can conclude like this: for the proposed system, that is introducing the automatic devices, the proportion of gates idle time is 25%, but it should not exceed 10% according to the given problem. So among the two conditions, one condition is satisfied, that is with the existing arrival rate and service time, the expected number of customers in queue should exceed 5, that is satisfied. But the other condition is that P naught, the probability of idle time, should not exceed 10%, but it is not satisfied. So the proposal of introducing automatic device cannot be justified. Now we can extend this problem like this. As per the given conditions, for the new service time, of 30 seconds, if we really want to implement the automatic devices, what should be the mean arrival rate of customers? Because the rate of arrival of customers goes on increasing with the passage of time, in the sense with years. So what should be the optimal level of mean arrival rate which will satisfy that LQ, that is expected number of cars in queue, is greater than 5 and probability of idle server does not exceed 10%, that is 0.1. Now for this we have to take the proposed service rate, which is 120 vehicles per hour, and for probability of idle server not to exceed 0.1, we can write 1 minus lambda by mu prime is less than or equal to 0.1, and solving this we get lambda greater than or equal to 108, which means that if the mean arrival rate of cars or vehicles is equal to or greater than 108 per hour with the service rate of 120 vehicles per hour, we get LQ equal to, that is expected number of vehicles in queue, equal to 108 square by 120 into 120 minus 108, which is 8.1. Now for the proposed system also, the expected number of cars in the queue is exceeding 5, and at the same time P naught is less than or equal to 0.1, that is 10%. So the mean arrival rate of customer should be greater than or equal to 108. So this is how we can solve the problems which comes in our real life situations. So thank you very much. In some other video I'll explain some other interesting example problems in single server queuing model. Thank you.